Hello, everyone. I'm Lara from Iprosima, and I'm going to host this new Artificial Intelligence Integration Working Group. Thank you very much for attending. Today is the kickoff of the working group, and the following meetings will take place every last Tuesday of the month at the same time. The same meeting room will be maintained throughout the time, and it is the same meeting room as in the embedded working group is used. In the document I'm sharing, I would like you to write down your name on the attendance list. So now I would like to introduce this new working group. The objective of this Artificial Intelligence Integration Working Group is to review the current state of the art of machine learning in ROS2 community in order to lay the foundations to start a standardization project. We'll be focused on enabling machine learning technologies for ROS2, applying artificial intelligence to use case in the new Vulcanexus framework. We'll talk about two amazing AI projects, ALMA and Sustained Machine Learning. Let's go to, wait a minute. Here. Okay, here is the agenda for today. So ALMA Project is human-centric algebraic machine learning. Algebraic machine learning, AML, is a relatively new machine learning technique based on algebraic representation of data. Unlike statistic learning, AML algorithms are robust regarding the statistical properties of the data and are parameter-free. And the Sustained Machine Learning project is focused on how to save and resource during the life cycle of developing AI models or machine learning environments, reducing the CO2 footprint. And after, we'll see a use case about serving models to ROS2 robots. So let's go to introduce our talker, Raúl Sanchez. So welcome, Raúl.
Hello, everyone. Thank you, Lara.
Okay.
Okay, so as Lara already said, I'm Raúl. I'm the project manager of the Artificial Intelligence group here at Proxima, and I will be presenting today, as Lara already said, the ALMA project, the SustainML project, and also we briefly cover a use case on how to serving models on ROS2 robots using the new Vulcanexus framework that Proxima is launching. So first, I will start presenting my screen. Okay. So as I said before, we will start with the ALMA project, which is the human-centric algebraic machine learning project. Then we will move forward to the SustainML project, and then we will finish with enabling machine learning technologies for ROS2. So starting with the ALMA project, first of all, I would like to talk about what is the ALMA mission. The mission of the project ALMA is to provide a new machine learning paradigm known as algebraic machine learning, which will be easily understandable by users. So we will try to avoid this black box phenomenon that currently it's taking all the neural networks technologies. Will ease the interaction of human AML technology. We'll also try to seamlessly integrate this AML technology into ROS2 using this AML integrating platform, which is a platform we'll try to integrate AML into ROS2, as I said before, and also doing so, we will ensure long-term maintenance of AML environments. So I will like to highlight some of the partners in the ALMA consortium. So, for example, the FKI, which is one of the leading research institute on artificial intelligence. Also, we count on INRIA, which will focus on the research of human AML interaction. Then Champalimaud Foundation and Algebraic AI, which are the founders of algebraic machine learning. Then BTT is focused on how to apply ethical issues and cultural issues to AML and how to embed all those topics into something that AML understands. Then the Kaiserslautern University will be in charge of developing software and hardware acceleration for AML. The Carlos III University and Firewall Foundation will try to apply this machine learning technology to real-world scenarios. And finally, Eprosima, which is the company leading this project, is in charge of developing this AML integrating platform tool and is in charge also of incorporate this AML technology into the ROS2 ecosystem. So first of all, I would like to present the AML comparing this new technology with the traditional approaches to machine learning. So starting with symbolic AI, symbolic AI use formulas to describe the world. However, it has some difficulty to learning from data, but it has a high transparency. On the other side, we have the statistical learning, which learns from data, but has some difficulty using formal description of the world. And it's usually more opaque than symbolic AI. We propose algebraic machine learning, which describe the world using formulas. Also, it can learn from data and can combine data and formal description in order to provide a higher transparency to the user. Then, continuing with this comparison, the symbolic AI uses symbols, which represent real-world objects, and mostly uses discrete mathematics. Those symbols are permanent in symbolic AI. Also, on the other hand, statistics learning uses parameters, and these parameters can map to the world or intermediate internal descriptions. And mostly use continuous mathematics, and those parameters can change. Here we propose algebraic machine learning, which uses symbols, and these symbols can map to the world, which are translated to constants, or some intermediate internal description, which we call atoms. We will also use discrete mathematics, so we can create new symbols, and those symbols can change. So these are the main features of algebraic machine learning. First of all, algebraic machine learning is less sensitive to a statistical feature of training data, as we are not using any statistical approximation, as we are applying complex algebra model theory in order to be able to learn from data and formal description. Also, there is no trade-off between memorization and learning, as so we don't have overfitting as the current traditional machine learning algorithm has. Also, it has a higher mathematical transparency regarding all the outputs that we have from the engine, from the AML engine, and from the machine. Also, AML is thought to be used for large-scale distributed learning, so we can have many algebras learning in parallel, and all of them can be combined in order to create a higher-level model, in order to create a better model that just one algebra could do, because they all can share the atomization results and the learning results. Also, it's an interactive machine learning paradigm, as we can see the output of the machine. I mean, what are the machine actually learning, and we can change the parameters in order to change how the machine is processing the data and processing the formal description that we enter into the engine. So these are some of the proven cases that we've already presented in the ALMA project. The first one is the handwritten digit recognition in which we use the MNIST dataset. And here, what you see in the boxes is the actual atoms that the algebra is learning in the learning process. Then we also have the queen competition problem, in which we learn here the algebra learns from formal knowledge. So all the rules are encoded in the algebra, and the AML understands the game from the beginning of the learning process. We have also the use case of classification of human motion, in which we have the opportunity to apply learning from formal knowledge and also data taken from the sensors. Here I would like to present also some of the ongoing case studies. The first one, which is conducted by INRIA, is the interaction with a gesture keyboard. So here we can see how the human can interact with the AML engine and how these interactions can be made. Also, we have some steps into the robot control and path planning. And finally, we are also focused on how to embed world models and complex description of real-world concepts into AML. These real-world concepts include some ethical and also some cultural aspects. We've already published some papers regarding all these ongoing use cases that you have available in the ALMA website. So what is the contribution of ALMA to ROS2? So we will develop an open source decentralized AI integrating platform which will be compatible with ROS2, and this AI integrating platform will try to will focus on clouds and edge computing environments, trying to connect robots deployed on the edge with the higher processing computing processing server deployed on the cloud. Also, we will extend all those improvements into the robotics and constrained devices platforms, being ROS2 as the primary robotic platform. And we will also develop some open source experimentation tools for the ROS2 community. So as soon as we have some viable product for the AI integrating platform, we will let you know, so you can try to play around with this new platform. Also, Proxima is bidding on this on AML as the key disrupting AI technology for robotics, and we will try to integrate AML into the ROS2 public subscribe framework, being compatible with this one. So that's everything from the ALMA project. Maybe I went too quick for the AML or the algebraic machine learning algorithm, but in case you have any doubt regarding this, we have some extra documentation for you to have a more mathematical background. So you can contact us. Lara already gave your email in the agenda, so please send her an email so we can discuss AML if you want. So I would like to continue this presentation with the SustainML project. This project hasn't started yet. It's scheduled for the upcoming 2 months, so it will start on September. And let's start with the mission of the SustainML project. So the mission of this project is to provide a new sustainable and interactive machine learning framework developed for green AI that mainly will comprehensively prioritize and advocate energy efficient across the entire life cycle of the application, and avoiding AI waste. I will explain a little bit more of this framework as we progress on the presentation. Also, in the consortium of this project, we count on the FKI. As I said before, they are one of the leading AI research institute here in Europe. Also, INRIA is taking the side of the framework and human interaction. And yeah, we can on some other research institute as from France, the Copenhagen University from Denmark, IBM in Switzerland, and here at Spain, Proxima is coordinating the SustainML project. So how does the SustainML framework will work in the future? So first of all, the developer will describe the problem, the machine learning problem. So the developer will describe the task to solve this specific application, machine learning, artificial intelligence problem. So the framework will analyze all these tasks, divide and encode the problem into an abstract functional semantic. So all the tasks will be encoded internally into this framework. Then we move forward on the interactive process of the SustainML framework. First, the framework will suggest a machine learning model with knowledge transfer and recycling from its collection of neural networks knowledge cores. Then, once the framework provides this model suggestion, the developers can reconfigure the model with other cores, with optional pre-trained parameters, or design their own models. And this is what we refer to as the interactive design process. Once the developer have reconfigured the models, then we can move also into another model suggestions, and again, come back to the reconfiguration process. Once we have the model, the framework will convey the top-tier AI expert experience by suggesting the best practices and more efficient alternative for avoiding previous negative results, because the framework will understand the developer's problem. So the SustainML framework is not yet another AI studio tool, because a SustainML project will focus on investigate the detailed footprints on computing and data hardware, and develop novel hardware accelerators optimized for different layers and operation. Also, the user will see the estimated CO2 footprints, hardware resource, and training time during the design process. And this is important because we can estimate all the cost that we can incur in our machine learning application lifecycle before this cost actually occur. And then it will be useful for any user with any kind of knowledge. If you're a novice, then the framework will explain you the functionality of different parts of a neural network and why certain models structures are better suited for some specific task. However, if you have intermediate or expert knowledge in machine learning, you can leverage the SustainML framework to develop efficient models optimized for your specific goals. And finally, if you are an AI researcher, you can skip the problem describing process and just use the framework to benchmark and optimize the machine learning models' carbon footprints. So that's all from the SustainML project. As I said before, this is a project that will start in 2 months. So you will get more details on this SustainML framework as soon as we are making some progress on it. So now we are moving forward to the third point of this presentation, which is enabling machine learning technologies for ROS2. Here, I will present a simple use case on how to incorporate machine learning in ROS2 nodes and how this use case can be enhanced, or also how can you implement this more easily with some new tools that we are incorporating in the Vulcanexus framework. Also, I will explain a little bit about what is Vulcanexus and what what is included. So first of all, regarding the use case that I'm presenting, here we have a local area network in which we have deployed a ROS2 robot and some server. So the ROS2 robot is just taking some images and publishing those images to this server. The server has an already trained machine learning model which performs some inferences on the data that the ROS2 robot is publishing. So after the inference is performed, then this inference server will publish the data again to the ROS2 robot and this data will contain the prediction output. All of this is implemented using the services feature of ROS2, in which the ROS2 robot create a request on the inference server, and in this request it includes the image ID and also the image. Then the inference server will publish the response to that request, publishing the label of the request of the image and also the accuracy of the prediction. I haven't said this before, but the problem that we are solving here is the one regarding the MNIST dataset. So we are inferencing on handwritten digits. So here's the code. On the left side, you have the client application or the client ROS2 node, in which we create the client on the inference service, and we perform the inference request. On the right side, we have the inference server node, and here we create the service on the inference service also, and yeah, we're setting here the inference callback in order to create the adequate response to the ROS2 robot request. So up to this, here's the use case that I've already presented. ROS2 robot publishing some raw data, some images to our inference server, and then the inference server making the response with the prediction. So what I would like to go further and see what happens if we have some more distributed scenario in which we have one local area network in which we have deployed the ROS2 robot. Let's say this ROS2 robot is using 4G, 5G to connect to internet and publishing some images. Then on the other side, we have other local area network developed, implemented in the cloud, and here we have our inference server. So using ROS2 as using the default configuration, this cannot happen. So here we introduce the DDS router. So the DDS router is a new product, a new software that will connect seamlessly all the ROS2 robot on one LAN, on one local area network, to another local area network through the internet. The only thing that you have to configure is where those DDS routers are hosted, and also these DDS routers should be reachable on the internet. So I think that on the embedded working group already, some colleague of mine already presented the DDS router, but for you that are new on this AI integration working group, I will try to briefly summarize what the DDS router is and how are we going to deploy the DDS router in order to be able to adapt to our inference or serving model scenario. So going further with the DDS router main features, some of them are described here. The first one is that it allows one communication over TCP. It's designed for distributed DDS networks in which you have highly distributed ROS2 robot networks in which you have several robots in one location and some others in other. Then you can deploy the DDS router on both locations and then connect those DDS routers in order to communicate all those robots. Then it will implement efficient data routing, so we will avoid all the copies that can be made within the DDS router. The DDS router will just getting all the data coming from the local area network or from any ROS2 robot that you have publishing data, and then will forward all this data to the network or through the internet without performing any copies. It's very easy to deploy. You only need to configure the DDS router using a YAML configuration file and setting the listening address of this DDS router or the connection address to which the DDS router is connecting to, and that's all that you have to do. And then we allowed a topic like whitelisting, so you can filter out which topics that you want to transmit over the network. So let's say that, for example, you are using you have a ROS2 robot deployed on your local network, and you only want to transmit some alarm topic. So you can use the DDS router to filter this topic over the network, and then the only thing that you will get in the other side of the communication is this topic. It will also can be used to deploy a client edge cloud scenario, and this scenario is very similar to the one that we are presenting in our use case, in which we have on the edge some ROS2 robots communicating over DDS, which is the communication standard that ROS2 uses. All the data will go through the router will connect to the cloud server, and then in the cloud server we have another DDS router listening for incoming data. Then in the cloud we can deploy some monitoring tools like Prometheus, Grafna, and also even the fast DDS monitor, which is another tool that we have for for monitoring ROS2 networks. And this also can be deployed in any cloud framework like CodeShip, Kubernetes, or even Amazon Web Services. So once I've explained the DDS router, we are coming back to the scenario that I've presented in this serving model use case, in which we had the first the ROS2 robot in one local area network publishing some data, and in this case we deploy two DDS router on the edge of its local area network. So in the first one, the first DDS router will gather all the images from the ROS2 robot and will communicate those images over the internet to the second DDS router. The second DDS router will take all the information and transmit it to the inference server. Also, the same process applies back to the ROS2 robot from the inference service, in which the server will publish the inference result. It will reach the DDS router, which communicates to the other DDS router, and finally the ROS2 robot will get the prediction output or the inference result, as the ROS2 robot and the inference server are on the same local area network. However, we are currently working on supporting services on the DDS router, and this feature will be available in the upcoming week. So this is everything from the DDS router and how to connect a ROS2 robot with a server using deployed on different networks. Then I would like to move forward to the AI integrating platform. So here we have the same AI integrating platform. We will behave differently if you're deploying this on the server side or on the edge side. So on the server side, it will simply you will be able to simply train machine learning models, or even publish some models to the edge robot in case you want to perform the inference on the end device. On the edge side, you can also install these models published from the cloud. You can perform some inference and some classifications just calling an API, and then also it's thought to publish all the collected data to the server side in order to improve the model and also retrain the model with new data from the edge. So this is the use case that I've presented before, but now I'm configuring it using the AI integrating platform, or how we are thought to implement the AI integrating platform in the future. So on the left side, we have now the ROS2 robot. Now it's a robot swarm in which we have many robots deployed, and each of them is using the AI integrating platform. The AI integrating platform comes with the DDS router underneath, so all the communication and all the configurations that previously you have to manually perform on the DDS router to be able to connect to the cloud, now it's automatically done with the AI integrating platform. Then, so the only thing that you have to configure here in the integrating platform is the data that you are going to publish, and then the data that the ROS2 robot is collecting, in case you are applying the same use case that I'm presenting here, which is the serving models and serving already performed inferences on the inference server deployed on the cloud. Here's another scenario for distributed learning, completely separate from the previous one, in which we have the same. We have the ROS2 robot and the train server. However, in this case, instead of publishing the inference, we are publishing the model. So, for example, let's say that you have your robots already deployed, and you don't want to update the model that you have upload to the ROS2 robot. So, what the integrating platform will support is to be able to download the model from the server. So the server will automatically train the model with the new data gathered from the ROS2 robot, and then once you think you have the performance on the model that you want, then you can automatically distribute the model over all the ROS2 robot that you have already deployed, and using the AI integrating platform. Also, this can be applied to a collaborative training cluster in which you have several training servers. So if you want to create some replicas of your own training server, or even create some of them with different models, then the AI integrating platform will also support that. So as I said before, everything comes in Vulcanexus. Vulcanexus is a framework that Proxima have already released, that comes from with ROS2, with the latest version of ROS2. We support right now Galactic and Humble, But the main point of Vulcanexus is that you will have the DDS router, the AI integrating platform, and some other tools from eProsima up to date within the package that we deploy. So, for example, if we perform or improve the DDS router or the AI integrating platform using Vulcanexus, you will be able to automatically update your framework and use the latest version of this software. So, as I said before, it will be it's easy to download and configure. We provide Dockers for that, and also we have an installation manual in our website in order to for you to explain how to install Vulcanexus. But the main thing here is that we follow the same steps as you do to install ROS2. So you don't have to learn anything new if you want to play around with Vulcanexus. You can also customize your experience with ROS2 using, as I said before, some eProsima tools like the DDS Router, the AI integrating platform, which we are developing now, the fast DDS monitor or ROS2 monitor if you want to monitorize your network and your communications. And yeah, also it will allow one communication out of the box using the DDS router, and it's fully synchronized with fast DDS updates. So that's everything from me. If you have any questions, Lara, I don't know if you want to continue here.
Yes, if there is no questions, I think there are no questions. Okay, thank you very much, Raúl, for your talk. Well, that's all. So I want to thank everyone for attending, and I hope you found it interesting. And remember, next month we'll be here, the last Tuesday of the month, with many interesting topics. So please stay tuned. Thank you and bye.